Hello everyone, welcome to this lecture number 6 of NPTEL lecture titled Charging Infrastructure. Before starting this lecture, let us recap what we have studied up till now. So, we have studied the various introductions or various nomenclatures related to EV charging system, and after that we started discussing about things related to AC-DC converters, and in AC-DC converter the simplest converter we were revisiting, which is single phase diode bridge rectifier. In single phase diode bridge rectifier we have seen half bridge configuration of the rectifier. So, we have seen that the single phase half bridge rectifier feeding the resistive load, and we have seen that how this particular converter works, and we have also derived some of the expressions like the average output voltage or average voltage which will be appearing across the load. And we have also seen one important thing, which is in this particular circuit the power is being supplied to the load only in half the cycle, that means in the positive half cycle when the diode is forward biased, while in the remaining half of the cycle the diode will be reverse biased and will be blocking the voltage, entire source voltage across it. So, we have also defined some of the ratings by which which is governed by the circuit or governed by the external circuit, which helps in deciding which diode to be selected. And once we define this voltage and current ratings, like which voltage and which current to be ratings of the diode to be selected, among that family the diode with required forward voltage drop and diode with required dynamic resistances can be selected. So, in this we have seen the peak repetitive reverse voltage which this diode has to block is nothing but Vs peak, which is the peak of the AC voltage which is been applied, and the average current which will be going through the diode is nothing but dependent upon the resistance RL, which is actually being put at its output, and the RMS current is nothing but Vs peak by 2 RL. Now, in this we have seen that if we see the current waveform, let us write down some of the key points, like what are the key points and understanding we obtain from this half bridge configuration, diode bridge configuration. Let us see that. So, the first thing which we have seen, that the source current, or you can say the power is being delivered, the power is being delivered to the resistive load only in positive half cycle. Further, the output voltage is pulsating, or you can say that is varying between 0, if you can see, is the output voltage is varying between 0 to the peak value which is equal to Vs peak, and then coming down to 0 again. So, the output is pulsating in nature, output voltage is pulsating in nature, and the output voltage or the average output voltage, average output voltage the average output voltage is proportional to Vs peak, which is the applied voltage, which is the peak of the applied voltage. That means the average output voltage is only dependent upon the input applied voltage or input AC voltage or peak of the input AC voltage. It is independent, or there is no other way by which you can control that average output voltage. And you can also see from the figure that the current is only been drawn in the positive half cycle, while it is 0 in the negative half cycle. So, you can say that the current drawn is not continuous. So, these are the some of the inference we get from the single phase half bridge diode rectifier. Now, let us revisit single phase full bridge rectifier. Single phase full bridge rectifier. Now, let us see what is the circuit and how this circuit works, and let us try to draw different waveforms in the circuit, different critical waveforms in the circuit. So, the single phase rectifier is again having a AC voltage source, and then you have 4 diodes connecting in a manner as shown over here. And it is again being supplying to the load RL, which we have seen in the case of half bridge rectifier. So, again this is D1, D2, D3, D4, and you have Vs, which is nothing but Vs peak sine omega t. It has been connected to the midpoint of the 2 diode connecting in this manner. The current which is going again is determined as the ID, and the voltage coming across this as nothing but Vd, and the average voltage, if we do the average voltage, we will get the average value of the DC voltage which is being applied across this resistance. Now, in this particular circuit, if we see, instead of single diode, in the previous case we have now the 4 diodes, and in this 4 diode conducts in such a manner that it will allow the power to be delivered also in the negative half cycle. Now, let us understand the functionality of this single phase full bridge rectifier. In this case, when, let us see first the case when Vs is in positive half cycle, or you can say Vs, instantaneous value of Vs is greater than 0. During that point, what is happening is this particular potential will be at higher voltage or will be at a higher value as that of this particular potential at that particular point, as a result of which this diode is forward biased, and since this is at a higher potential is applied across this cathode of this diode will be reverse biased. Since this is forward bias, this particular thing will get connected, as a result of which the voltage which is applied over here will be coming over here, will be applying over here, and as a result of which the D4 gets forward bias, and since D4 gets forward bias, the D3 will get reverse bias. So, let us see what will happen is that D1 and D4 gets forward biased, and D2 and D3 gets reverse bias. Let us draw the circuit, how it looks like. See, D1 is forward biased, D2 is reverse bias, similarly D3 is reverse bias, D4 is forward biased, and then you have the resistance RL ID P sin omega t at that particular point, and the voltage across this is Vd. So, as a result of which, what you will see is that the input voltage which is there, which is in the positive half cycle, will be directly coming across this resistance RL, and there will be current drawing through this current RL. Let us also define the current drawn from the source as Is. That is when we can write that my instantaneous value of Is is nothing but equal to Id, which is been going into the load, and we can also write my Vd, the output voltage which I am getting, is nothing but equal to the instantaneous value of the voltage Vs, which is been applied from the source, from the AC source, because your D1 and D4 is forward biased, as a result of which the voltage across this is same as whatever the voltage which is been there in the voltage source, and because of this voltage there will be current Id, and because of this current, the same current will be flowing through the will be drawing from the source, which is nothing but an Is. So, that is why we will get this particular condition. Now, let us see what will happen when Vs is in negative half cycle. Negative half cycle means your Vs value is less than 0. When your Vs value is less than 0, that is when you will see that your D2 and D3 is forward biased, sorry, D2 and D3 is forward biased, while your D1 and D4 is reverse biased. So, let us draw the circuit and see. So, the circuit will look like this is D1 is forward bias, so D1 is D1 is reverse bias, D2 is forward bias, and your D3 is forward bias, while your D4 is reverse biased. However, if you look very carefully, your Vd voltage which you are getting in this particular case is nothing but minus of Vs, and your Is value is nothing but minus of Id, because this voltage will be now applying across this Vd in a reverse manner, because you see, if you are having a Vs voltage, this phase of this phase P and N point, or P and N terminal of this voltage source, this P is connected to the negative of Vd and your N is connected to positive of Vd, that is when you are applying the negative of the AC voltage which is been there. So, let us draw, by understanding this particular, by having this understanding, let us draw the particular waveforms of the circuit. So, let me take the waveforms of the circuit. So, this is your first, let us draw the Vs. Now let me draw the voltage Vs. This Vs will be having a sinusoidal variation. I mean, obviously we have the AC source. Now if you look very carefully, this is our Vs sin omega t. Vs, since the Vd, as we mentioned over there, let me also write down the conditions when Vs is positive. My Vd is nothing but equal to Vs and Is is nothing but equal to Id, while when the Vs is negative, my Vd is nothing but equal to minus of Vs and Is is nothing but minus of Id. So let us draw the Vd waveform, or the waveform or voltage waveform which will be appearing across the load. So let us draw the Vd waveform. Since in the when Vs is positive, Vd is nothing but equal to Vs. So let me draw the Vd equal to Vs. The same way, the way the Vs is drawn, the same way it will be following the same pattern we have drawn the Vd. And in the negative half cycle, however, in the negative half cycle, Vd is nothing but the negative of the Vs, which is nothing but, if you draw, it will be like this shape. So this will become just the opposite negative of that. So this will become like this. Similarly, at this point again you have the same waveform, and at that point again you have the same waveform. So what we see is that the Vs is having positive polarity and negative polarity, however Vd has just the single positive polarity. However, this is still in the pulsating nature. This particular Vd will be applying across the resistance RL. Now since this Vd is applied across resistance RL, the current through the resistance RL, which I have defined as a ID in the circuit, will be also be following the same pattern. However, let us try to, so this is nothing but my ID. So Vd ID. Since my ID is of this shape, let us see what is my Is. So Is is nothing but equal to Id when the Vs is positive. So this is nothing but equal to Id when Vs is positive, and it is equal to minus of Id when it is the negative half cycle, or when the Vs is negative. So let me draw the negative of that, and then again it is positive, and then again it is negative. So this is nothing but Is, the current drawn from the source. Now if you look very carefully, this current drawn from the source is having a sinusoidal variation, and it is having a unity power factor, which means that the current source voltage and the current drawn from the source voltage is in the same phase. And if you try to draw the this different values, so this is Vs peak, this is again Vs peak, what we get, this value is nothing but again Vs peak, this particular value is nothing but Is peak, this value is nothing but minus of Is peak, this is nothing but Is peak. Similarly, this is Vs peak, and this value is nothing but peak value of Id, which is nothing but, we can write Id peak, which we can write down over here as well. This is nothing but Id peak. So Id peak is nothing but the Vs peak divided by RL, and Is peak, we can define that as a Vs peak divided by RL. So, with this we understood that how the voltage which will be appearing across the load in case of full bridge rectifier, and what will be the, I mean, how the current will which will be drawing from the source. Now, in this particular thing, if we try to calculate some of the aspect which is, let us try to see how, I mean, different components in the circuit, I mean the different aspects of the circuit looks like. So, let us first calculate average voltage of VD. Now, this average voltage will be applying across the resistive load RL. So, this average value of VD we can do again the same way, since if you look very carefully in this particular circuit we have the time period which is T given here. Now, this particular VD repeats itself after half of the cycle of your supply voltage. That means if you are applying a 50 hertz input, so if you are applying, if your source voltage is varying at 50 hertz, so your Fs is let us say 50 hertz, then your T is nothing but 1 by Fs, which is nothing but 20 millisecond. And accordingly we can write that omega is equals to 2 pi Fs, that means we can write omega T is equals to 2 pi. And if we see carefully, after every T by 2 time it repeats itself. So, it is not the case in case of half bridge where the VD repeats itself after the total time period T. In this case we are the voltage, the output voltage or the VD voltage repeats itself in every T by 2 time. That is why we are writing, we are trying to find out average over the T by 2 period. So, it is 0 to T by 2. We will again write the value which is Vs peak sin omega t dt. If we do that, it will become 2 by omega t minus V peak cos omega t 0 to T by 2 overall 2 Vs peak by omega t minus of cos omega t by 2 minus cos 0, that will be 2 Vs peak omega t we can write directly 2 pi, this will be minus of minus 1, that way if we do calculation it will become as 2 Vs peak by pi. Now, this is the average value of the voltage of the DC voltage which is been applied across the resistance RL, and that average voltage will be somewhere, if we draw in the circuit, it will be somewhere in the range something here, which is nothing but average value of VD, nothing but 2 Vs peak by pi. So, this is the average value which is exactly double the value which we get in the case of half bridge, single phase half bridge diode rectifier. In this case, in case of full bridge, we are getting double the voltage, since the power is being delivered in both the positive half cycle and negative half cycle of the input voltage. So, let us see the diode selection criteria. I mean, again it is the same ratings which will be defined in this. Here our VRRM, which is nothing but the peak repetitive reverse voltage, which is nothing but, if we look very carefully, during this time period it is D1 and D4 is conducting, in this time period D2 and D3 is conducting, in this time period again D1 and D4 is conducting, in this time period D2 and D3 is conducting. Since in this time period D1 and D4 is conducting, and in this period D2 and D3 is conducting, and in this period again D1 and D4 is conducting, in this period D2 and D3 is conducting. Since in this period D1 and D4 is conducting in the first half cycle, as a result of which this D1 and D4 is on, and as a result of which this VD voltage which is there at the output will be appearing across this D2 and the D3, because if this is on in this entire loop, this voltage is getting dropped across this diode D2. Thus, we will see that the VRRM is nothing but is the VD peak, which is nothing but equal to the VS peak. So, that is why in the while selecting the diode, one must make sure that the diode must have the peak repetitive reverse voltage of Vs peak. And if we see the average current through the diode, so IF average. Now let us see for the diode D1 and D4. Now when we see diode D1 and D4, it will be conducting, it will be only conducting during this period, while this in this period it is not at all conducting. So thus we can write their average value as 1 by T, 0 to T by 2, Vs peak sin omega t by RL, because it is feeding by RL because it is feeding to the resistive load, and then we will do this. So this when we solve this particular expression, what we will get is we will get Vs peak by pi RL. This expression we have already solved in the case of half bridge circuit case. So the same expression we are deriving here. So which we get Vs peak by pi RL. Similarly, in for the D2 and D3 also, IF average D2 and D3 also, if you do, it will be 1 by T, T by 2 to T, Vs peak sin omega t by RL into, the integration over T by 2 to T, and it will again gives you Vs peak by pi RL. So the average forward current of the diode is nothing for again for D1, D2, D3, D4 is nothing but Vs peak pi RL. It only depends upon the value of the load which this bridge rectifier is supplying and the input voltage which is been applied at its input. Now let us also see the IRMS rating for determining the I square T rating of the diode. So let us also see the IRMS rating of the diode, which is again can be calculated 1 by T, 0 to T by 2. Again for the D1, D2, D3, D4 the whole thing will remain be true, Vs sin omega t by RL whole square dt. Now this when we try to solve, we will get a value Vs peak by 2 RL. Now this is the IRMS current which is going, or RMS value of current which will be flowing through each diode, and that's when you can define the I square T rating using IRMS value, where T is the time period for which it is conducting. In this case our T will be 10 millisecond. So accordingly one can define the I square T rating as well. Now let us see what we understood by this particular converter. So let us try to find the inference from this single phase full bridge converter. The first and foremost thing we have understood that the output voltage is uncontrolled. That means it only depends on input voltage or only depends upon the input AC voltage. Vs peak, if you look, if we see here, the average output voltage is only depending upon the Vs peak. Second inference, we can obtain that the input current is sinusoidal in nature, as it is supplying the resistive load, that is why it is having the sinusoidal in nature. But one thing is it can be seen that the power is delivered in both the cycles in both the cycle means positive and negative cycle to RL or to the resistive load. And one thing is, we can see that one more thing we can see that the output voltage is not constant, it is actually a rectified DC voltage, or you can say rectified DC voltage. That means the output voltage will be varying from 0 to Vs peak, then coming back to 0 in the form of a half sine wave, and then again it goes in the same variation. That means you can say that your Vd of t is nothing but your Vs of t, modulus of Vs of t. It is of that particular form, and it is continuously varying. It is continuously, it is not constant, it is continuously varying. So this is the inference we get it from the full bridge rectifier, and by understanding, by seeing the operation of this full bridge rectifier, these are some of the references we can obtain while revisiting the full bridge rectifier, single phase full bridge rectifier. In this particular case, since it is supplying to a resistive load, we could able to get the sinusoidal current drawn, also the power is been delivered in both the cycles. However, the voltage, the output voltage is not constant, and it is continuously varying. So we have seen how the single phase half bridge rectifier works. We have also seen how the single phase full bridge rectifier works. We have inferred some of the critical information which will be used by us in future to understand why the kind of converter which are being used presently in while doing the AC to DC power conversion in a EV charger looks like, why we will derive that particular converter, and we will understand that. So to understand how we will reach to that particular converter, it was important for us to understand and to infer some of the critical points from while revisiting this diode bridge rectifiers. We have understood that we could able to get the input current in the form of sinusoidal when we have the load which is a pure resistive load. We have also understood that the output voltage which we get from this half bridge and full bridge rectifiers are uncontrolled. That means we cannot control the output voltage, we can only it is only dependent upon the input AC voltage. That means one has to vary the input AC voltage, which is not the case in majority of the cases, because the input is directly from the grid. And we have also seen that in case of full bridge rectifier, the power can be delivered to the resistive load in both the positive as well as the negative cycle. And we can also see that the output voltage, we get the output voltage in the DC, we get the DC output voltage. However, that DC output voltage will be keep on varying, it will be keep on continuously varying from 0 to the peak value, and then coming back to 0. So thus we will see in the next class or in the next lecture how we can get the constant DC voltage at the output using the single phase full bridge rectifier with a capacitive filter. and we will see, we will derive again, we will derive and we will see what are the problems that particular converter brings in, and that is when we will move ahead. Thank you for patiently listening to this lecture. We will see you in the next lecture. Thank you.